Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to general class. This episode is subelement G9, question group B, and I'm your host, Ron Call, KE7CR. This question set is about antennas and feed lines. So let's jump into the questions. The first question asks, what is a characteristic of a random wire HF antenna connected directly to the transmitter? You need to realize that wherever the connection is from the transmitter is where the power is being fed out from the transmitter to the antenna. So power being a combination of current and voltage, the current at that point is going to be high. The current at the ends of the wire is zero. There's no current moving. So the current changes along the length of the wire. So if you have a wire connected directly to the transmitter, current is going to be high right next to the transmitter, zero at the end of the wire. So you're going to have the possibility of carrying significantly high RF current right next to the transmitter. If the impedance is matched, that power should radiate off the antenna just fine. But if there's an impedance mismatch and some of that power is reflected back to the transmitter, you could get RF current building up on the chassis of the transmitter. And as you touch that, you could get RF burns. So you need to make sure that your station is grounded well, chassis is grounded well, so that you don't have that possibility of RF burns. The next question asks, which of the following is a common way to adjust the feed point impedance of an elevated quarter wave ground plane vertical antenna to be approximately 50 ohms? The best way is to slope the radials downward. Remember, a vertical antenna, top half represents basically one half of the dipole antenna. The radials are the bottom half. If it's an elevated vertical antenna, those radials can be sloped downward to change the impedance. The next question asks, which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? This image, if you're watching the video, shows, imagine the vertical antenna through the center, and the radio waves radiate off the antenna. But notice they're going along from the wire. So at the ends of the wire, they're not radiating at all, up and down. They're radiating outward horizontally. That direction is called the azimuth. When we talk about directions, azimuth represents like north, south, east, west. Elevation is how high of an angle from the horizon. Straight up is 90 degrees, zero at the horizon. So this pattern is called omnidirectional in azimuth. It's radiating equally well in all directions, north, south, east, west. The next question asks, what is the radiation pattern of a dipole antenna in free space in a plane containing the conductor? So I like this image. Imagine that the conductor is the green line shown here. So say that's the antenna wire. That's represented on this image behind the donut. So you can see the green wire, say that's the antenna. The radiation pattern is going to be essentially a figure 8. That's the red line shown here. Or if the antenna wire is this horizontal red line, then it's shown by the figure 8 green pattern here. So the answer to this question, it is a figure 8 at right angles to the antenna. The next question asks, how does antenna height affect the azimuthal radiation pattern of a horizontal dipole HF antenna at elevation angles higher than about 45 degrees. So we're talking 45 degrees up to 90 degrees straight over your head. If you lower that antenna down closer to the ground, more of the radio waves are going to bounce off the ground and reflect back up, changing the figure 8 pattern. Say instead of this nice figure 8 pattern here, some of the radiation bounces off the ground, comes back up. It's going to smooth that out. It's more omnidirectional, just a straight circle heading straight up. So the answer to this question, if the antenna is less than a half wavelength high, the azimuthal pattern is almost omnidirectional. Next question, where should the radial wires of a ground-mounted vertical antenna system be placed? Now, if you're on the ground, the radial wires will have to be placed on the surface of the ground or buried a few inches below the ground. When I put up a vertical antenna, I used my edging machine that I edge my lawn with to just dig a slight trenches into the ground and bury the wires there. I've heard some people put little staples to cover the wires until the grass grows over the top of them. But the answer is on the surface or buried a few inches below the ground. The next question, how does the feed point impedance of a horizontal half-wave dipole antenna change as antenna height is reduced to 1/10 wavelength above the ground. Because radio waves are going to reflect off the ground, recombine with the radio signal, you're going to get some traveling back down the antenna wire. It's going to change the impedance of the antenna as you change the height. So as you decrease the height, you're going to decrease the impedance. Just remember that. Decrease height, also decrease impedance. So the answer is it steadily decreases. The next question is similar in a way, but it's how does the feed point impedance of a half-wave dipole change as the feed point is moved from the center towards the ends? So you can have a center-fed dipole and power radiates off each half of the dipole. If you switch to closer to one end or the other, an off-center fed dipole, the feed point impedance steadily increases. The impedance is lowest in the center, higher towards either end. So if you move towards one end or the other, the feed point impedance steadily increases until at an end-fed dipole, impedance is highest at the end. The next question asks, which of the following is an advantage of using a horizontally polarized as compared to a vertically polarized HF antenna? And the answer is lower ground losses. A vertical antenna, you're going to have ground radials, you're going to radiate some of that energy directly into the ground. It's not going to radiate off the ground well. But a horizontal antenna placed above the ground, those radio waves are going to reflect off the ground, and some of them will recombine with the radiating radio waves to actually enhance that signal strength, and you have less ground loss both ways. The next few questions ask about the lengths of antennas. The basic formula to remember here is 468 divided by your frequency in megahertz. 468, who do we appreciate? Just remember that. Take 468 divided by your frequency in megahertz, and that gives you the length of the antenna in feet, the approximate length of the antenna in feet. The first of these questions asks, what is the approximate length for a half-wave dipole antenna cut for 14.250 megahertz? So you take 468, divide that by 14.25. The answer, 32.8. The closest answer choice to that is 33 feet, so that's the answer. The next question asks, what is the approximate length for a half-wave dipole antenna cut for 3.550 megahertz? So again, it's 468 divided by the frequency in megahertz, 3.550. And the answer is 131.8. The closest answer choice is 132 feet, so that's the answer. The last question asks, what is the approximate length for a quarter-wave monopole antenna cut for 28.5 megahertz? Now it's a quarter wave, so if we take 468, that's going to give us a half wave, just cut that in half. So we'll do 468 divided by 28.5 gives us 16.4, but let's divide that in half to get the quarter wave antenna length, and that's 8.2. The answer choice that's closest is 8 feet. And that's the end of this section. I hope you learned a lot this time, and look forward to you in the next episode. 73, this is KE7CR.